By the addition of a new axle with a 9 1/4 inch diameter drive gear to the previous 7 1/4 and 8 1/4 inch units, we now have a family of 3, basically the same in design and with minor variations the same in servicing procedures. As in the other 2 axles, the 9 1/4 inch unit has a cast iron integral carrier housing with steel tube axle shaft legs pressed into the carrier and welded in place. The drive pinion in all 3 axles is supported by 2 preloaded taper roller bearings seated in the carrier housing. Both bearing cones are a press fit on the pinion shaft and are separated by a collapsible preload spacer. Drive pinion depth of mesh in the 7 1/4 and 9 1/4 inch axles is determined by the thickness of a shim between the pinion head and the rear bearing cone. In the 8 1/4 inch axle, the adjusting shim is located under the pinion rear bearing cup. Differential bearings are positioned by turning threaded adjusters at each bearing cup in or out as required to preload the bearings and set the drive gear backlash. The straight rollers of the axle shaft bearings in 8 1/4 and 9 1/4 inch axles ride directly on finished journal surfaces on the outer ends of the shafts. C-washer locks on the inner ends of the shafts restrain their outward movement. The permanently lubricated axle shaft ball bearings in the 7 1/4 inch axle are pressed on and held in place by a steel collar. A retainer plate at each bearing restrains outward shaft movement. The axle drive gear ratio is stamped on a tag located at one of the cover screws. 7 1/4 inch axles with the tag under the cover screw nearest the filler plug have differential gears which are different from those used in axles with the tag at the bottom. In either case, the gears must be replaced only in complete sets. Axles normally make sounds which are typical of gear operation, so don't jump to the conclusion that all axle sounds mean trouble. Normal gear sounds may be disturbing to some, but experience has shown that this condition seldom results in a breakdown. And since sounds from other sources, such as tires, can be mistaken for axle noises, the actual cause in each case should be identified as closely as possible by using the road test and diagnosis procedures described in the service manuals. Abnormal sounds within the axle are either bearing or gear noises or combinations of both. Bearing noise is a continuous growling or grating sound which may increase or decrease with changes in load and speed. In comparison, drive pinion and gear noise is distinguished by its periodic nature. This is more of a tone than a grinding sound which may be heard only within a certain speed range on either drive or coast. If the diagnosis narrows down to gear noise, incorrect adjustment can be the cause, and a gear tooth contact pattern test is the best way to check it out. To run a tooth contact pattern, drain the axle, remove the cover, and wash the gear teeth clean to prepare for the test. Also, disconnect the propeller shaft so you can use a wrench to turn the pinion and drive gear under a test load. Brush the drive gear teeth evenly with a light coat of yellow iron oxide or titanium white paste. If the coating is too thick, the pattern will smear. To get a distinctive pattern, we put a friction load on the drive gear by prying against the rim of the differential case or by partially applying the parking brake with the drums in place. With load applied, turn the pinion to rotate the drive gear 1 full turn in each direction. If you rotate the gear more than this, any pattern variations will average out and cover up indications of excessive gear or pinion runout. Now, if the pinion depth and backlash settings are correct, the most distinctive part of the contact pattern should be near center on both the drive and coast sides of the teeth. When the gear and pinion are under actual working load, the tooth contact area spreads out, especially toward the heel ends of the teeth, which explains why a good contact pattern should be near center under a test load. If the most distinct part of the pattern runs off the teeth or is near the top or root, it indicates a tooth overload and interference condition, which produces noise and can result in chipping or other tooth damage. The tooth contact pattern is not acceptable if it is way off center on both sides of the gear teeth, usually as a result of incorrect pinion depth setting, or if the pattern changes location around the gear because of excessive runout. Where the tooth contact is high on the heel end of the drive side and also high on the toe end of the coast side, a thicker shim is needed to move the pinion in toward the center of the drive gear. This moves the tooth pattern toward center and downward. In comparison, Where tooth contact is low on the toe end of the drive side and low on the heel end of the coast side, the pinion must move out, away from the drive gear center, so a thinner shim is needed. This moves the tooth pattern toward center and upward. Gear backlash, which is far out of adjustment, also contributes to a heel and toe pattern. However, since the effect of backlash on the pattern is small, changing this adjustment will not correct a condition where re-shimming is necessary. When the heavy part of the pattern moves back and forth on the teeth around the gear, it usually indicates an excessive amount of runout. If the pattern repeats itself approximately 3 times around the gear, the pinion is the probable cause. If the pattern movement repeats itself twice on opposite sides of the gear, the problem may be in the drive gear or the differential case. Repositioning may help to reduce gear runout, but excessive case runout calls for a new part. Checking or changing the pinion depth shim requires pinion removal. Here, as when installing a new pinion or bearings, we use the axle pinion setting gauge tool to determine the correct shim thickness to be used. After removing the differential pinion shaft, push the axle shafts inward so the C washer locks can be removed. Pull both shafts completely out of the axle, being careful not to damage the shaft seals. To clear the way for pinion removal, the differential assembly must be removed from the carrier. Mark the bearing caps for proper replacement. And remove the bearing adjuster locks. Loosen the bearing cap bolts so the adjusters can be turned easily, but do not remove the bolts at this point. Insert the adjuster tool through the axle tube on each side and loosen the adjusters to clear the bearing cups. Then remove the bearing caps and the differential assembly, keeping the bearing cups with their respective cones. On the 8 1/4 inch axle, the threaded adjusters should be kept with the bearings, but the adjusters in the 7 1/4 and 9 1/4 axles remain in the housing. Next, measure and record the existing pinion bearing preload for reassembly reference. Read the bearing load as you slowly rotate the pinion with an inch-pound torque wrench. The reading may be 0, but there must be no bearing end play. Now, remove the nut and lock washer and pull the flange off the pinion stem using a removing tool. If you pry out the pinion oil seal, be careful to avoid burring the seal recess edge. The pinion is driven out of the front bearing cone. This results in damage to the bearing, so both cone and cup must be replaced with new parts. Discard the collapsed preload spacer so it will not be reused by mistake. In the 7 1/4 and 9 1/4 inch axles, the adjusting shim between the rear bearing cone and the pinion head must be removed for checking. The shim under the rear bearing cup in the 8 1/4 inch axle must also come out. With the shims removed and a new front bearing cup in place, you install the axle pinion setting gauge tool in the usual manner. Remember that the setting tool is also used to seat the bearing cups in the carrier. The correct pinion shim should fit between the gauge block and the crossbore arbor of the tool with a definite drag. The next undersize shim should pass through easily, but the next oversize should bind. The shim you select will be correct only if the pinion end is marked with a 0. Where the pinion has a plus mark, you'll have to use a shim that is thinner by the amount shown after the mark. Where the pinion is marked with a minus, you'll need a thicker shim. Minus before a 0 is a production mark and should be ignored. After the selected shim is installed, slide on the new preload spacer and position the assembly in the housing so the new front bearing cone can be pressed on with the installing tool. Drive the new oil seal in place and press on the pinion drive flange with the same installing tool used for the bearing cone. Tighten the flange nut to 210 foot-pounds minimum torque and then measure the bearing preload with an inch-pound torque wrench. Carefully continue the tightening and measuring process until you reach the specified preload and no farther. Exceeding the preload limit can cause bearing overload failure. Where the nut is tightened too far, you'll have to repeat the preload process with a new collapsible spacer and complete new front bearing. Don't try to reduce excessive preload by backing off the pinion nut because it may loosen when under working loads. With the pinion in place, carefully position the complete differential assembly in the carrier housing. Install the bearing adjusters if removed and put the bearing caps back in their original positions. Screw in the bottom bolts until their heads are seated finger tight and tighten the top cap bolts to 10 foot-pounds. Gear backlash and differential bearing preload are adjusted together. Insert the bearing adjusting tool into the axle tubes alternately and turn each adjuster until bearing end play is eliminated with about 10 thousandths backlash remaining. Remember that differential bearing cups do not always move directly with the adjusters, especially when an adjuster is backed off. So the bearings must be stabilized by oscillating the drive pinion 1/2 turn in each direction, 5 or 10 times, each time the adjusters are moved. With a dial indicator, find the point of minimum backlash by checking at 4 positions, approximately 90 degrees apart around the gear. When this point is located, index the gear and pinion so the same teeth can be meshed when completing the backlash adjustment. With the gear at the minimum backlash position, loosen the right adjuster and tighten the left, reducing the backlash to 3 to 4 thousandths of an inch, with each adjuster tightened to 10 foot-pounds. Stabilize the bearings and tighten the differential bearing cap bolts to 45 foot-pounds on 7 1/4 inch axles and 90 to 100 foot-pounds on the other axles. Now, alternately, tighten the right adjuster and stabilize the bearings until you reach a constant torque of 70 foot-pounds on the 7 1/4 inch axle and 75 foot-pounds on the others. This should set both the bearing preload and gear backlash. Final backlash on 7 1/4 inch axles should be 4 to 6 thousandths and 6 to 8 thousandths on the others. After the final backlash adjustment, rotate the drive gear to the other 90-degree checking positions. Backlash at each point should not be less than the smaller figure specified, but can vary by 3 thousandths of an inch between the minimum and maximum. For example, if the minimum is 8 thousandths of an inch, the maximum can be 11. Now, if the backlash is correct and the preload at both bearing adjusters remains constant at the specified torque when the bearings are stabilized, the adjustment is complete and we can install the adjuster locks. To double check your work, run another tooth contact pattern test to prove out the pinion and backlash adjustments. If everything is okay, the axle can be built up and except for a final road test, the job is finished. The procedure given in the service manuals for overhaul and service of the 9 1/4 inch and related axles add many details we're not able to cover here. Be sure to review your reference books for this session and watch for the session on basic door and body adjustments coming up next.